Hi, welcome to a new topic of basic electrical engineering. As we know, the syllabus which covers Unit 1, it is common for all the sister allied courses of engineering under CSC, Computer Science Engineering. Likewise, you have AIML, you have data science, you have cyber security, you have computer science and design, and you have computer science and business systems. This syllabus is common to all the JNTUH related institutions. So we have already dealt with Unit 1, that is DC circuits, where we have seen the concepts of basics of circuit elements, that is passive elements RLC, active elements voltage source and current sources, and we have also discussed about KVL, KCL, and we have analyzed the importance of mesh analysis and node analysis using different approaches of mesh and node. And then we have solved some numericals based upon superposition theorem, Thevenin's theorem, and Norton's theorem. Especially in today's class, we are going to see time domain analysis of first order RN and RC circuits. So this is the common syllabus for all the first years of JNTU students. So we'll continue with the topic, that is time domain analysis of first order RL and RC circuit. First, we'll start with RL circuit. You can see a series RL circuit is provided with a DC, that is V in. You can have n number of responses. Instead of DC V in, you can have a step response or you can have a ramp response. Anyhow, we are going to see the basic which is involved with the DC, or you can analyze with a normal step response also. So for this circuit which is shown in figure 1, you have to apply KVL in clockwise and you're going to get equation 1, and this equation 1 is nothing but the algebraic sum of the voltages in a closed network is equal to 0. So the supply voltage, that is V in, is equal to the drop across the resistor, that is Ri, and the voltage developed across the inductor. So equation 1 you can change it to equation 2, which seems to be a resemblance with the differential equation. And this differential equation, when you compare with the mathematics, it is a kind of non-homogeneous differential equation. In mathematics, you have two types of equations under differential circuits. So for that is homogeneous equation, you have the dx by dt plus px is equal to 0, and for non-homogeneous equation, you have dx by dt plus px is equal to q. So equation 3 and equation 5, these are the equations and their general solutions are given by equation 4 and equation 6, where equation 4, it is for the homogeneous equation, which is nothing but the complementary function, whereas the homogeneous non-homogeneous equation, which is given by equation 5, for that we have a general solution which is given by x of t. It is a composite of particular integral and complementary function. Anyhow, we said that equation 2 resembles to this non-homogeneous equation. So we'll take this into the account and we'll apply the general solution, which is I of t, and here p value is nothing but r by l and q value is nothing but v in by l. So we are going to apply the integration and we are going to cancel out the like terms. Then we are left over with equation 7, which is nothing but v in by r plus k e to the power of minus r by lt. So K is an arbitrary constant and this is obtained with the initial conditions. We are assuming here that the inductor doesn't store any kind of energy. So initially the current through the inductor is 0. If that is true, the conditions we are going to take the current that is equivalent to 0, and we'll frame the values of t, that is 0, and we'll get the value of k. So applying this equation which is obtained in the form of k in equation 7, then we are going to get I of t, which is nothing but v in by r of 1 minus e power minus r by l t, and this we are treating as equation 9. Now equation 9 is in a form of equation which has the resemblance of getting the waveform which is exponentially rising. Okay, here we are going to consider a time constant which is equal to L by R. This is for a series circuit, and the time constant for a series circuit which is in RL, that is given by L by R. So we'll take the values randomly, that is when the small t is equal to tau, that is L by R, then the value of I of t would be 0.632 V in by R. So this is the value what we get when we substitute the value of small t is equal to tau. Likewise, you substitute different values of tau, that is 2 tau, 3 tau, 4 tau, and 5 tau, and these are the values which are going to get when you are going to substitute for small t. Based upon these values, if at all you draw the graph which is shown in this figure 2, it is exponentially rising. So this is the exponential rising curve that is generally for a RL circuit which is series applied to a source, input voltage source. Based upon this equation, you can calculate the voltage drop across resistor, which is equal to V in of 1 minus e power minus t by tau. And roughly, we are going to get the exponential curve, that is the voltage drop across resistor, which is again an exponentially rising curve. Similarly, you have the formula of voltage developed across inductor, which is given by this formula. So apply this I of t over here and differentiate it. We are going to get the value of VL of t, which is nothing but equal to V in e to the power of minus t by tau, and roughly you are going to get the exponentially decaying curve, which is in this fashion. I hope you understood this particular logic, how we have framed figure 3 and figure 4 based upon the voltage developed across resistor as well as inductor. Now we'll take the case of RC circuit. Again, we assume that there is some input voltage which is driving RC series circuit, and when we apply KVL, we are going to get this equation which is framed as Roman 1. And if at all I consider the conditions, like if at all I take V in as an input voltage, the resistor voltage drop is R I of t, which is nothing but given by small VR, and Vc, that is the voltage drop across capacitor, that can be determined by assuming the conditions of Vc is equal to 1 by C integral it. This is a general formula of voltage developed across the capacitor. Now this voltage we are treating as Vc of t, and I can obtain the value of current by differentiating this equation on both sides as C dVct by dt. So these all assumptions I'm going to take as equation 2, and then I substitute equation 2 in equation 1. Then I'll get V in is equal to R, which is nothing but this resistor, multiplied with I of t. This I of t is nothing but C dVct by dt plus Vc of t. What I'm trying to do, I'm trying to frame the equation 3 in a non-homogeneous equation which is shown in 4. Now again, this is a non-homogeneous equation. For this, the general solution we know, we have already seen from the mathematics analysis. And when apply this general solution for determining the capacitor voltage for different value of t, I'm going to get Vc of t as V in plus k e to the power of minus 1 by RC t. Now we can determine the value of k like what we have done with the RL circuit. So the k value here, it is obtained to be minus V in. In fact, the voltage across capacitor is obtained to be V in of 1 minus e power minus t by tau. What is this tau? Again, it is a time constant. So here the time constant is RC. For RL it is L by R, and for RC it is RC. Now when we substitute for different values of t as tau, I have framed this tabular column. Now based upon this tabular column, if at all I draw the graph, again I'm going to get the same graph, exponentially rising. But mind you, this exponential curve is the voltage developed across the capacitor. Unlike the inductor, that was the current developed in the inductor RL circuit. So from this figure, we have framed the equation 7 in the graph form, and we can also determine the developed current as well as the voltage across resistor. Now you can see I have from second equation, third and eighth equation, I have just replaced the value of equation 8, and I have differentiated, and I substituted the current equation, that is I of t, and that is obtained to be V in by R e to the power of minus t by tau. Now that is the resistance drop is obtained to be R I of t, which is nothing but equivalent to the equation which we have framed as V in multiplied with the equation E of minus t by tau. Now if at all you try to draw the graph for this two equations, that is the current equation as well as the voltage developed across the resistor. This is how it is obtained, which is shown in figure 7 and figure 8. So that's all for today's class. I hope you like this class. Please go to the description. I am attaching a PDF which is going to give you the information of syllabus, which is for unit 1 from starting to the ending, so that you can see and cover your syllabus, and based upon that you can solve different numericals. And that's all for today's class. Please share among your friends, subscribe to this channel, and press the bell icon for the future notifications. Thank you.